Evening YouTubers, it's Sunday night again and welcome back to the episode 3 of ShrigleytubeTV. In tonight's episode we've got, starting off in the dyno cell, we've got this engine which is a 998 R17 fast road imp engine, and we're going to do a little bit of a touch on ignition advance and why it's so important. And then we've got a snippet about one of my customers, a customer who came to me for a head retorque on his police imp. So that was a nice little quirky thing to see. So I've done a bit of a video on that. Not the retorque, just the car. And then also we've got Oulton Park Gold Cup on Saturday. So I'm going there. I'm going to take some pictures, some stills, and try and get some video footage of some of the old stuff racing. There's all sorts of old historic F1 stuff and special saloons and all sorts. So we'll get some of that on and I'll get it all loaded up for Sunday night. And then to finish off, we're going to do a session on the 5-bearing block with the new head. And we'll have a chat about that, but we'll save that to the end. So hopefully you guys all stay on board to the end of the show or program. Right, ignition advance. Something that is massively overlooked. Most engines I get to dyno, the ignition advance curve is just totally wrong. They're all doing an advance dead early in the RPM range, and the engine carries on revving to like 8.5, but it's finished advancing by 4. So what I do is I tailor the advance curve to suit the engine and where peak torque is, and then what it does afterwards, etc. Because it's up there where the engines live when they're in the car, so that's the important part. I'm not going to go into how I do all that. I'm just going to touch on and talk about ignition advance, because I know there'll be people on here who are 10 times better educated than me and will be like, what is he on about? But I'm just trying to touch on the basics here for the masses so that you've got an idea. So I'm trying to turn all my viewers into race engine engineers. That's the plan. Right, so we've got our piston, we've got our spark plug, and we know that we have to have ignition advance. And the reason we have advance, which when I say advance, I'm saying the spark plug sparks the mixture, the compressed gases and fuel before the piston gets to top dead center. And the reason we do that is time. It takes time for the burn to get going and to do what it does and expand the gases and push the piston down on the power stroke. So your ignition advance is critical that we get it so that the burn starts before top dead, and then just after top dead center, it's really starting to expand the gases and it can push the piston down and we can make the most of those energies. That is the critical point. Now, as an engine the clever bit is as an engine gets faster, it can run more advanced because we've got less time to do it. We can spark it earlier to get the most out of that burn, and that's where it gets a bit tricky. Now, I've done a bit of a video, which you'll see in a minute, of this engine, and I did something what we call a dizzy swing. Now, when I did my apprenticeship with Bob Jones at B&J, he used to always have me on a dizzy swing in the dyno cell, and I used to hate it. He used to set me up with my earmuffs and my face mask, and I'd go in the dyno cell and he'd be screaming the nuts off something, and he'd be like, give it some more advance, and I'd be like holding the dizzy and trying to get the advance into it and watching the torque meter, and you basically get to see what we try and go for a peak torque, which is where the engine's most efficient. What we do is we get it to peak torque, wide open throttle, say it's doing 65 foot-pound of torque, and we'll always start by reducing the advance. So we take the advance out of it to see if it hurts it, or see if it helps it. If it helps it, great. We don't want to be putting more in because we could start it detonating and then we could do some damage, especially if it's a high compression race engine. It doesn't take long to knacker the job. So yeah, we're going there and I'd do the dizzy swing, and basically what I'd be doing is I'd be finding exactly where the engine wants that spark to start by moving where the spark starts from, basically, because by moving the distributor I'm affecting the advance, I'm affecting where that spark starts to ignite the combustion, the gases. And anyway, this is how it works. It's just rough thing. This runs at half speed, so the crankshaft's doing 1000 RPM, this is doing 500. So if we have 10 degree swing on here, which means it starts at one place and finishes 10 degrees further, it ends up at 20 degrees at the crankshaft. So all my dizzies tend to have a 10 degree swing in the dizzy, and that equates to 20 degrees on the crank. So this one, in its finished state, it ended up with 20 degrees at idle and then it did a 20-degree swing at 6,000 RPM. It had 40 degrees of advance. That's a pretty standard sort of place to start and stop. And the way it does it, very clever. Well, it's very simple. There is also on some distributors a vacuum advance. We're not going to go into that. That's an economy thing. The ignition advance that we're going to talk about is the one inside the distributor, and it works by two little weights that's living here. And these bob weights, they fly out with centrifugal force. So the faster they go, they fly out, and they're spring loaded against the peg that drives the rotor arm. So this is independent. Obviously, you can see it spins on there, and it as the bob weights fly out, they advance. So it starts there and it finishes there. They advance the cam, so they move this round more, which means that the spark, as the engine goes faster, instead of it sparking, say, there, it starts sparking here. I mean, that's just an exaggeration. Now, the dangerous part with advances, on this engine, because it's 10.5 to 1, it's very numb. It's what I call a numb engine. It's not that fussy about its advance. But when you've got something that's got like 13 to 1, or like James's engine at 14 to 1, they are really sensitive, because if you start to ignite the burn, ignite the mixture before top dead center too early, and then it carries on compressing, we have a situation called detonation, where it's to do with the speed of the burn and the way it goes subsonic, or we're looking for a deflagration, but when you get a detonation, it's a different type of burn. So you get like a shock wave and a load of heat. So instead of the energy, I'll say the best way of describing it, instead of the energy being used to expand the gases and push the piston down, we get a situation where we get like a shock wave and a boom, and that can pick on the piston and either pockle it or push the gasket out. Worst case, if it's on for a long time, it'll pick on whichever's the hottest part, and the detonation will pick there, because obviously the hotter it is, it's a vicious circle basically. Once it starts detonating, it can't stop, because detonation induces heat, heat induces more detonation, and we just get a vicious circle, a spiral of decline until the whole lot's mush. So we'll often see the side of the piston melted where the gases have tried, the pressure's been so high, it's basically torched down the side of the piston. On the Hillmans, because they're such a short stroke, they're not that sensitive, because even though the static's high, the dynamic is quite low. So when you get into turbo, in fact, I could go on forever here. I just wanted to touch on the basics. We have ignition advance for a reason. It's overlooked. It's really, really important. It's as important as the fuel trim. So there you go. What I'm doing next, I want to run this. I want to do my little dizzy swing, find out where it's happy, and then I'll put the timing light on it so you can see how the advance moves. So you'll see the little blue line moving away, moving to and fro with the timing light, and then you can just give you an idea of how it all works. Okay. Right, you've just seen a video of this engine running under load. I'm basically holding it full wide open throttle, and although the camera didn't pick up too well, I am putting advance and a retard and looking at how it affects the torque. And like I said earlier on, being a low compression or relatively low compression engine, it's not massively ignition sensitive, so we didn't see massive gains and massive losses, but it did make a difference. And what you might not have picked up on was you could hear where it was happier with less advance. So that was a little bit of an insight into how the advanced system works on an imp engine. And next what I'll do is I'll put the timing light here so you can see how the mark moves independently. So we have our 10 degrees of movement with the rotor arm, and it's going to equate to 20 degrees here, and you'll see the numbers going from 20 to 40 degrees. Right, YouTubers, nothing to do with but we've got this little quirky thing here today. It's a police imp, a genuine one from 1964. I've just been out for a test drive after talking the head bolts down on it because he had the head gasket done and I had a retorque, and I've never seen so much smiling faces. Everyone loves it. So we'll have a quick chat with Paul. Look, this chap here has just pulled up in his car and started taking pictures. Paul, you're like famous.
I know, you can't go anywhere quickly in this thing.
No.
Don't ever plan to go Saturday to the shops. Because you come back Sunday.
I'm loving all the cones in the back there. They're awesome.
Yeah.
And you got a hat.
Well, originally, it of course only had one seat.
Right.
It only ever had one seat because they carried ropes and cones and all the other things in where you would normally have the other 3 seats.
Wow.
Just to give them the space.
How long have you had this?
5 years.
5 years.
And me and it are 2 weeks apart in the same birthday. It was built 28th to the 3rd, 64, and I'm 18th to the 4th, 64. And I know which one's wearing better.
Yeah. Well, I'm not retightening your head bolts, that's for sure.
There's the original. So the original radios in here, the old pie.
Yeah. And the helmet.
The original. Well, there's the custodian helmet. That's the original.
Oh, it's a proper hat.
Yeah.
Safety hat.
Yeah.
Yeah.
How old is it?
1964. You got more fans here now. Have a quick picture of a donkey.
All original, yeah.
Yeah, as it came.
Mad that, innit? Mad that these used to chase you, innit? Crazy, man.
Got some more fans. Right, Paul, well, thanks for letting us look around your car. I really appreciate it.
The daft thing is, if you speak to Durham Police about it, they sent us a lovely sheet about how it was used, because people say, like this guy has, you wouldn't chase anybody in it. It was designed to get you to where you started walking your beat.
Oh,
the
right.
Police station.
Yeah.
It says when you've walked your beat, you can stand next to the car, not sit in it, for 15 minutes while people approach you with any problems.
Wow.
Then you could get in and drive to where you start your next beat, hence why they've never done any mileage.
Amazing.
So in 59 years, this has got 52,500 on it.
Yeah. Flipping out. Well, I'd rather cruise that than a mini metro. That's what I remember them having when I was a young lad. They were all in mini metros. Yeah, brilliant. Right, thanks again, Paul.
No worries.
Let's hear the Nina. Right, I'm back again. Got something to add to that first part that I just did. I had a friend call in and I showed him the video and I said, what do you think? You know, he doesn't know an awful lot about engines. And he said, to be honest, Andy, I lost interest because you was going on about static and dynamic compression and you lost me. So I thought I'd just do a little bit more of a video just to explain them little bits to help you understand where I'm coming from. So when I talk about compression ratio, I'm talking about when the piston comes up, it's squashing all the petrol and air mixture into an area, into a space. Now the bigger that space it squashes it into, the combustion chamber, the bigger it is, the lower the compression ratio, because you've got the amount of ratios into that one area. And the smaller that area, the smaller the combustion chamber, the higher the compression ratio. And the reason on a race engine we chase compression is because the higher the compression ratio, the more volatile a burn is, hence the detonation if we go too high, you know, or spark it too early. Now, what I wanted to say was, all this works back from something we call the cylinder pressure. Now, you'll have all heard of a compression tester, I'm sure, where you hold the throttle open and crank the engine over and measure the compression cylinder pressures. So, this is where we come into static compression ratio and dynamic compression ratio. Everyone talks about a static compression ratio, which is what we measure on the bench, it's a dead simple calculation really. It's a swept volume, so this is a 998, so we'll call it 250 cc's of one cylinder because it's divided by the 4 cylinders. It's 250 cc's, and then you add to that the total chamber size, which on this engine was 26.2 cc's. So it's 250 cc's plus the 26.2. You add them together and that'll give you 276.2, and then you just divide it by the chamber size to give you a ratio. So it's 250, 276.2 in total, divided by the 26.2, and that'll give us 10.5 to 1, because I've written it on there. But I'll like a calculator, aren't I? So that's how we get a static compression ratio. But the reason I'm going on about this now is because a dynamic compression ratio is what the engine actually sees. So if you can imagine the piston has finished exhausting, it's finished bringing the inlet charge in, the inlet valve's shut, and I've got that wrong again, haven't I? Sorry. We've drawn the charge in, and the next time the piston goes up, the valves are going to be shut. But the inlet valve stays open for a little bit longer than past bottom dead center. So we only start measuring after the valve is shut, which the piston may have travelled 10-15 millimeters up the bore before the exhaust valve shuts, the inlet valve shuts. So in that time, this is where we get a dynamic compression ratio from. So it'll always be lower because it's actually only squashing for the time that the valve is shut, if you get me. So sorry I got that all muddled up. I should have practiced. So the static compression ratio is the full sweep, as in the valves aren't open or shut, they're just all fully closed. And the dynamic is taking into account the cam profile and for how much time that inlet valve is left open. That's why we get standoff. When you look sometimes, you'll see a bit of standoff. Anyway, we're not going to get into that. Right. And the example I wanted to give to you was, if we get a Hillman Imp race engine with 13-to-1 compression and a big race cam in it, and we put a compression tester on it, we will see potentially 220 psi of cranking cylinder pressure. But if we get, say, an old school MGB engine, a race one, with 11-to-1 compression and a milder cam than the Imp engine, because the MGB obviously doesn't rev the same, and crank that over, it'll be seen at 11-to-1. I'd imagine, roughly from the ones I've done, we'd see maybe 280, 290 psi of cranking pressure. So even though it's a lower ratio, static, its dynamic will be higher, because on an MGB engine, it's got like 80 odd mil of stroke, so it's squashing for all that area. Despite the valve being open for a bit at the bottom, we've got far more squashing. So that's why when you really want to get into these engines, you need to work everything back from a cylinder pressure, not from a ratio. But we're getting a bit into it here. I just wanted to give an example. So my example is full race Hillman engine with a short stroke, 13-to-1. We might see 220 psi of cranking pressure. Plodder MGB engine with loads of stroke, 11-to-1 compression, much less static, will have a higher dynamic because it's squashing for longer. Simple as that. So I hope I made that simple and not confuse you completely. And what my pal also said was, I was talking about the bob weights and the dizzy, etc. He said, that's great, but I'm a visual learner, so I need to see what you're talking about. So I've got a dizzy here. I'm going to put the camera on a zoom in. And then what I'll do is I'm going to hold the end of the dizzy so it won't move. So what I'll do is I'll show you the springs opening. Can you see these two weights on the outside? They fly out, and this here is a cam. So as that weight flies out, it turns the peg shaft, which the rotor arm sits on, and you can see the springs fighting it and pulling it back. That is where the advance comes from. So it's just like, it's very much like a governor on, say, like those old school engines from the Anston Engine Museum. Right, I just wanted to clear that up. I hope I haven't caused any more confusion. I'll speak to you soon in the next video, which will be, I think we're going to do some block skimming and some piston intruder making. Got a 998 wet liner block on the milling machine here, and I thought we'd do a little quick video just to show how the liners sink over time. So at the moment you'll see we've basically got no contact whatsoever, and what I'll do is I'll run the head over it, and then we'll look again and we'll see where it's contacted and where it's not, and you'll see where it's sank them. Right, just finished doing the first pass with the milling with the fly cutter on this 998 block, and I'm really pleased to say, well, I did sort of know this was going to happen because I could already see the liner was low with my straight edge. Now, if you look, you'll see the tip is cleaned up all the way around, and it has all gone all the way that end as well. But if I move the table that way, it goes dark because this end of the workshop's a bit darker. But I pulled it this way so you can see. So we can, if we look, the top of this liner has cleaned up all over, but this one, it's barely kissed and it's not touched it around here. So that one was sat a little bit low. And what we'll do next is we'll put another 5 thou on, and hopefully it'll clean up another area. Now this timing cover wasn't perfectly matched. I can't feel anything, it's probably just about level. It's probably just a couple of thou down. You can see the shine there from where it's been face plated in the past, and that's the fresh material that's been machined. So another 5 thou on it, and we'll wazz it across and see what it looks like. Right, okay, we've just finished the final pass, and I'm pleased to say that everything has touched on now, so we're good to go and go to the next stage, which will be cleaning. We're going to face plate it, get all the high edges off, just deburr this little edge here, and then I'll get it all clean. And then I think what we'll do is, because I know this block has been skimmed before, because it's been a 998 for a while, it's an original sort of old school race engine, the new pistons we're going to put in it will protrude. So I will go through the process of making the pistons level with the top of the block, and because we're always chasing compression ratio with these engines, we'll make the pistons into little intruder pistons. So I'll go through that in the next video. Okay, so we've got the block that we just seen in the milling machine having the deck faced, and I popped one piston in just to get a piston height on the dummy build, and I can see that the piston is roughly 20 thou. We measure it across where the pin is. It's roughly, not saying 30 now, why is that doing that? 23. So I reckon if we say 22 thou proud, what I'm going to do is I'm going to machine exactly 22 thou for top of the piston so it sits level, and that'll give us our correct squish in the squish area on the head when we come to build it all up. So obviously this has a paper gasket around the outside, the wheel string sits in the middle here and in this groove, and then this is our squish band area, which that tolerance is really close. Really important that the piston gets to within 20 thou and then away again. That gives us a bit of room for stretch on the rod when it's doing big RPM. Now what I'm going to do with the piston is, first of all, I'm going to put in the lathe, clock it up, and we're going to turn around the outside 20 thou off it, and then I'll put it on the milling machine and we'll machine this area. And the idea of that is where this side here where the spark plug sits. No, it's not. It's this side here. Sorry. Right, it's this side where the squish area is, so that when the piston gets to top dead center it doesn't hit, and then all the rest of it will be a little intrusion that will go into this chamber. Now I know that 20 thou at 72.5 mil equals 2 cc's, so we're going to end up with roughly 50-60% of that left after we've machined around the outside and machined this part off. So we'll end up with about 1 cc of protrusion, which sounds like not very much, but when we're chasing compression, remember compression is the cheapest power you can find, so it'll be worth doing. Right, I'll get this piston in the lathe and we'll get machining it. Right, we have the piston ready to put in the lathe, and we're going to face just the outside to create clearance, so when the piston goes past top dead center, or past the top of the block should I say, we don't end up with it hitting the head. Now this is the first stage. Second stage will be on the miller, and I need to turn this. So what I'm going to do is I'm going to pop it in the chuck, but we're not going to clamp it with the jaws because it's really delicate and thin, and they're quite shallow, the jaws, so it could just potentially fall out. Pistons are a very special shape. They're bigger across here and smaller across there, but that's another story. Anyway, what I'm going to use is, this is a homemade drawbar that I use. So we're going to put this inside the chuck, and then this is a 15.8 mil sleeve tube, and this is obviously 5/8. So I'll use this, it's nice and loose, to pop into the piston, and then I will pop that through there, in there like that, and pull the piston back against the chuck face, and that will be enough to hold it whilst we machine it. We'll also have to clock it. In fact, I can probably do it while I'm talking to you. So that goes in there like that. I'll put the nut on the back, which starts to draw it back. And then what we do, get it a bit closer. Now this tool I've got in the tool post here is my favourite tool for doing these facing the pistons. It's got really big radius on it, so we don't end up with any sharp corners on the face, on the crown of the piston. It all ends up nicely radius, which is how we want it, because sharp corners are stress raisers, and we don't want a stress raiser on something that's getting a hard time in an engine because that's where fatigue starts. So I'm just trying to do this as quick as I can. Bring the drawbar tight. I'm just screwing the nut along the thread at the back. It's just getting there now, and hopefully when I let go the piston will stay put. Great. So what we need to do first, of course, is we need to clock it up. So we'll make sure it's in neutral. Just need a bit more preload on it there. Where's my spanner gone? Preparation, pour. Right. Okay. So what I'll do is I'll get the clock, and then, well, I'll say what, we'll just get the clock now. Now, we don't want to hit this piston with anything hard because we could damage it potentially. So what I'm going to do is I'm just going to use something really soft, like the wrong end of a hammer. So I look at my high point here, and unfortunately you can't see the clock gauge, but the clock gauge is giving me an indication of where to hit. Obviously it's pretty obvious at first because you can see it going round, but as it gets closer the clock gauge comes into its own really, because it helps me to see where I need to hit it to make it run through. And I'm not winning with this. Come on, I'm at about 10th now. Come on, shape Andy. You're on camera, we're live. Oh, well, that's good. Getting closer. Right, sorry about that. Just got myself in a bit of a tiz. Obviously conscious of the time, and you guys sat there watching thinking, oh my word, I'm going to fall asleep here. So I've clocked it up now, and as you can see, he's within a thou, which is perfect for what we want to do. So I'm going to put the camera back on the stand and we'll start machining. Right, I'm about to start machining. What we're going to do is start the machine up. I'm going to touch on the face, lock the bed up, and then I'll use this little cross slide here to get my 20 thou. So what we'll do is we'll just move this to an area where it's a bit stiffer. There we go. So we'll zero that. Then we'll go in, touch on, and then we'll lock the bed up. Now I want 20 thou, which is half a mil. So this is in metric. So we're going to go 0.4, which is 16 thou. So we'll wind him in gently. There. Oh, what I should have done was, from there, we'll go one full revolution, which is 5 mil. I'm looking for 5 mil basically. So that's 5 mil there. Let's just see if that's roughly where I want to be. Needs to be a bit further. Another couple. Okay. Let's see where that is. because I need 5mm clearance for the squish band before the radius. That needs a bit more. This will be on diameter and radius. Right, that should be us. Perfect. Right, and then obviously I've done 0.4, which was 16th thou. I now need to go to 0.5. I've got my zeros set on here, so it's a shame the camera doesn't actually get that bit. But anyway, I've set the 0 on the cross slide, which is there. So I know when I go back to this 0 point, I'll be at the same position again. Okay, so maybe we'll adjust the camera onto. There we go. Right. So we've got a traverse here. We lift this lever and it goes in on its own accord. So at 0.5, get to there. Watching for the 0 on here. Lovely. And then we need to just put a tiny edge on the top of the piston just to take that sharp edge off. So I'll zoom in again to get a better view. I'll just go in, going to go past the 0.5. Just put a nice chamfer on the edge of the piston. So that's the first stage complete. I'll do all 4 pistons now and then we'll get on the miller and do the tops. Okay, we've finished machining the pistons on a lathe. So all 4 now. I've got the perimeter machine back for clearance. And now we need to remove this area of material that's opposite the squish band. So obviously it needs to be off the piston so it doesn't hit the head when the piston's at top dead center. Now, to the trained engineers out there watching this video, this might look extremely dodgy, and that's because it is. But I've done it before. It doesn't harm the piston. I've got a light pinch on them, nothing massive. So it's just sat on the 2 flats at the bottom of the piston, and it's all sat nice and straight. So what I'm going to do is I'm going to fire the machine up, and I'm going to start gently tickling away until I get level, and that'll be my 0, that'll be my height, and I'll go back to that for every other piston then, so they're all like. We'll try again with the motor in gear. Right, okay. I can just see it's just starting to kiss around there. The piston's slightly low on that side, which isn't ideal. Right, I've just jacked him up a little bit on this side with some paper because it's just a little bit low there. And it's possibly because I'm operating the bed up and down without the lock on it, so that it may have just tilted slightly. So we'll, rather than tightening the bed up now and changing the settings, we'll just jack him up a little bit and we'll run him across now with a couple of thou extra and see if he cleans up all the way. Right, that'll do me perfect, that. We've got him to clean up all the way across. Feels great, that. We'll get it all cleaned up and I'll do a bit of zooming so you can see the piston properly. So this is the first piston completed now. You can see we've removed that extra material there and we've still got, I'd say maybe 40-45% of the piston protruding. We know that 75 mil by 20 thou equals 2 cc, so we've maybe got a cc if we're lucky, maybe 0.8 of a cc protrusion, which sounds like nothing, but with these small engines it's the small bits that count. And then I'm just going to talk about this for a second. This is very special to me. This is my fly cutter. When I first started out, I didn't have a fly cutter, so I made this on the lathe, and I was just looking at it before, and when I looked I realised I'd used a Hillman Imp front pulley bolt to hold it together. So done me proud, this has. These are all the different attempts I had at making it work. I didn't get the angle quite right on it, so I didn't have the clearance and it just kept on rubbing. But in the end we got there. So there you go, a little story about a bit of my history in the workshop. I've assembled the engine now with the intruder pistons in, and I've got a little test to do, which is really simple. It's just a piece of steel that I place on top of the block. Now I know that I can't come past the top of the block or the piston may collide with the head at high RPM, so I can see there that the piece of steel isn't being hit by the piston. I'll just check it all the way along, and we'll do the middle two next. Just what you've got to think is, when the piston is going really fast and it has to change direction at the top there, the stresses are massive. So even though it's below the deck and we know that we've got 20 thou clearance when the head's clamped on, because that's the crushed thickness of the wheels ring with the paper gasket, we've got to allow for a bit of stretch. Now obviously the first time it comes up, when it's compressing, it's got the cylinder gases and the burn to stop it from carrying on going this way. But when it's exhausting and the valve is open and it pushes the exhaust gases out, that's when it gets a bit stretchy, so we end up with it carried on going a little bit. So we do this little test to make sure that the pistons are low off the top of the block. So that's all gone really well. I'm dead happy with it. I'll carry on building the engine and we'll run it probably next time. Bit of a treat here, guys. I'm here with the Russell Meister at Oulton Park Gold Cup, and we just caught Steve Platts. Now Steve's raced this car for as long as I can remember, and it's really quick. He was like qualified third in his race, and I think he came out fifth overall. The car goes really well. Steve, are we okay for a quick chat?
Okay.
Okay. This is Mr. Platts. I've raced with him. If you watch my video from 2011, he's that red imp that shocks me up going into Old Hall and everyone commenting on that. But anyway, how long have you raced this for, Steve?
About 20 years.
Mate, it's got to be, I think it's more than that, you know.
I think it's 2004 when I started.
Oh, fair enough, you've got the date. Well, you've got the anger valve to make it go anyway, and you've got the reliability, absolutely. Yeah. But when did you come there? Fifth, was it, overall?
Well, today? Well, I was on the podium because they were in the T's.
Oh,
so
really?
I was second.
Oh, mate! Congratulations, I didn't realise.
Harry in a BMW.
Mate, you're flying the Hillman flag high, I love it.
Yeah,
Mate, and that little Ben Bolt engine flying. good, isn't it?
It is.
Is it 1150 that one?
No, 1120.
11 old school.
Yeah.
Yeah. Oh,
Well, that's how it came. So we didn't change it.
no. Why not? It works, doesn't it? You got a 5-speed box. And it's been a race car for a long time. So it's well tuned in, isn't it?
It is.
Right.
Gearbox, I did that years ago. We were working out which
Ratios. Do you change them for meetings or?
years ago I did, but these days no.
Maybe if I came back out with you, you'd have the competition and you'd be,
Yeah, maybe.
Well, we need to make our own imp grid and have our own imp race. That's what we want. That's what we need to aim for.
Well, it would be good.
Steve is chairman of the HSCC, but it's just struggling for numbers a bit, though, isn't it?
It is.
Yeah, it's very hard times for the clubman racer. But anyway, thanks very much for your time, Steve.
No
I'm going to do a bit of a look on the car. That's all right.
Keep on rocking.
Top man. Right, this is the Platzi-mobile. We call him Steve Splats because he used to hit everything, but we don't call him to his face because he gets upset. But look at that. Yeah, boys. Smile. Right. Peace out. I think that's Jonathan Farmer coming to empty the cash basket. What do you think, Dougie? That good? It's a helicopter, isn't it?
Somebody else, but
I'm just here now with Brian and the orange Anglia.
yeah.
We raced for a long time, haven't we?
Yeah.
Years ago. How long have you raced for, mate?
How long I've only been driving since 2000 because I'm diabetic.
Yeah. You had a break, didn't you?
Yeah, well I rolled it, didn't I? And I had to repair it, so it was a time there. But yeah, about 4.5 years altogether.
A break. But you're back at it now.
Yeah, back at it, all back together, and it's going well. The driver's not going well.
Mate, you
but,
were flying around and enjoyed
I was
it.
having good fun.
And the car looks absolutely awesome, mate.
Well, it does, doesn't it? That's the thing.
And tell us what happened in race 1, Brian. Go on, let's have the truth.
All right, okay. Put about 5 litres too little fuel in it.
5 litres too little. Oh, mate. Did you get to the end?
No, that
Oh,
was the
oh,
thing.
you-
I would have won the class as well.
Oh, mate.
I won the second race. I won the class. Purely because I was the only one in it, but there you go. A trophy is a trophy.
Mate, well done. And when we're next out?
I'm intending to go to Croft in about a month's time.
Brilliant.
I won't be there, I'm afraid.
No,
but-
that's a shame.
Mate, it's nice to see you and it's nice to see the car out again because that's
Well,
brilliant.
it's trying to generate the interest for people to come and do it and see it and perhaps say, oh, well, where can I do that?
Tough times for the historics at the moment, isn't it?
It
Really
is.
tough. Yeah, it's a shame. It's just it's so expensive, isn't it? Right, guys, it's Friday. I've got the head here that I wanted to talk to you about that I mentioned in last week's episode, where we've got this posh new steep inlet angle head that was originally developed by the Roots competition department back in the day, like in 1965 or whatever. Now, I've been having a chat with my posh mate, well, I say posh, clever, we'll call him Clever Will Parry. And I said, Will, where am I going wrong? I said, I've been messing about these for ages. So we've got a bit more mid-range out of them, made them a bit friendlier. But we're still stuck. If we see 110 horsepower, we're like having a little party, you know? I said, and a rubbish one with no compression and old school everything does 100 horsepower still at like 8.5. So what do you think the problem is? And he said, whatever the limiting factor is, you can't find it. So I thought, oh, that's a good point, yeah. So we reckon this is the answer. Because we think that, we know it's not piston speed, that's well down. We know it's got good frictional losses. We know most things about the engine. But like the Americans always work back from a horsepower rate on the head. You give an American guy a head and say, what do you think of that? He'll go, that'll flow 300 horsepower. They all work it back from a flow rate. Now, maybe that's where we should, well, it is where we should be going with this head, really, sending it away to somebody who can measure the airflow and give us an idea of where we're going to be with it. I'll pull the camera off in a second and we can have a closer look at it. But it's so interesting that, you know, if it is an air thing and it just can't get the air, you know, what I have learned, not wanting to give too much away, is that valve size on big lift engines isn't, on these big lift engines, on the imp engine with the traditional head, isn't so critical. And I'm beginning to think if the valve isn't the issue, it's the port size. So obviously everything's a trade-off. We go bigger on the port, we will lose down the bottom, but you know, I'm hoping this new shape of port is going to be so much better. It's very much like an athlete, and we were discussing like an athlete's limiting factor is his VO2 max, which is, well, one of his factors is basically how much oxygen his body can absorb, and it's pretty similar to an imp engine really. These are his nostrils, and he's limited by the amount of air we can get in. Like I always say to people that always want to argue with me about it, the air is waiting to go in there. We just got to put the piston below it to create that vacuum for the air to go in there. We are under 1 bar atmosphere. We've got 14.5 psi waiting to go through that hole. We just got to give it a reason to go there. So yeah, I'll pull the camera off, we'll have a quick look at the head, and then that'll be it. Right, we've got the head on the bench here. This is the new deep angle head we're going to be using on the 5 bearing bottom end. Obviously this is as it's come to me, so I've got a lot of work to do on it yet. You can see straight away compared to an imp head, which is something I should have prepared. Right, I'll get an imp head. As we have one handy here, you can see compared to the imp head, the angle is totally different. So looking at it as a visual straight away, the first thing it strikes me is instead of going inlet exhaust, they've gone exhaust inlet. So we've got a bit of messing about to do there. Obviously the cam profile is different, so nothing can interchange there. But the best bit, what I'm really excited about, I mean, this is up at 30 mil already, this, and bearing in mind we struggled to get to 28 with ours. Just look at that for an inlet port. Look at the angle on it, it's beautiful. The turn at the bottom, it's so high, it'll turn beautiful through there. Hopefully the air will just love to go around that corner into the cylinder. So there's the inlet manifold as well. Obviously this is all angled so as it's set up on an imp. It's a really good condition casting, to be fair, and the inlet valve is pretty enormous. You know, we're on a 1.5 inlet on this. Now I'm gonna have to do a bit of messing because we're going to put it on a bigger wheel string groove, so I'm not quite sure. Might get it laser welded yet. I don't really want to put a lot of heat into it, but you'll see there, it's absolutely gorgeous. You know, put the torch on that side. It's really nice. I think it's going to work really well. And there's not much information on the engine. All I can see is, obviously it's been welded end to end. It's obviously had a bit of a crack at some point, but if you look there, it's 4 for the 7th, 1966. So I don't know who that would have been for, but I assume that was the date it was put into production or ready to go racing. So also it's on a 5 bearing cam carrier and it's on a big follower. So yeah, I'm actually having the carriers remade as a 3 bearing. I'm going to run a steel cam in them rather than the old chill cast, because we're going to put some proper lift on this, and obviously with the RPM it sees as well. I just want to make it absolutely, you know, idiot proof, so that it can take no end of abuse, and we can do some winning races with it. So that concludes this week's episode. I hope you've enjoyed it. I hope I've not bored you and gone on too much about things, and I will look forward to speaking to you all next Sunday. Bye for now. I'm back again just for 30 seconds. I just wanted to say, if anybody out there has got an opinion or knows somebody who worked with these deep cylinder heads back in the day, has any evidence, we've got a few pictures of them already on cars and stuff, that can support their use in modern day historic racing, or if they want to tell me what will work and what won't work before I go through the pain curve myself, I'd be really interested to hear from them. So you can either contact me in the comments section, or you can email me at ShrigleyEngineering 998@gmail.com. Thanks very much. See you next week.